Welcome back to Bytes of Pi. Today we're going to cover part 1 of recursion. In today's video we're going to be covering recursion, infinite recursion, and base case. We'll also be able to trace simple recursive programs. Recursion refers to the programming practice of having a method call itself. Here's a simple function that demonstrates recursion. We're going to cut over to Eclipse and trace through this function. Here we are, we're already in the debug mode, and we're simply calling, here we are in the main function, and we're going to be executing foo for the first time. And we're going to call it with a value of 1. Stepping through it, we print out what's the value, and then we call itself, and I'm going to increment it by 1. So this first time through, x is equal to 1. Stepping through, and now x is equal to 2. I'm going to print out 2. I'm going to call it x is equal to 3. Print out 3. X is equal to 4. I think by now you'll see the problem with this function. This is called an infinite recursive loop. All recursive definitions must have a non-recursive part. A definition without a non-recursive part, like what we just showed you, causes infinite recursion. That means it'll keep on going till it gets out of memory, or we'll have an overflow issue. The non-recursive part or point of a recursive function where the recursion stops is known as the base case. So what do we mean by the base case? Well, here's the same function, but we're adding an additional statement to make sure that the function stops. So notice we'll keep looping until x is equal to 4. Okay, we're going to start off with 1 again. We're going to step into it. We print out 1. 1 is less than 4. It'll keep going. 2 is less than 4. Keep going. 3 less than 4. And so on. Until we hit the end case where x is greater than 4. And then it stops where x is equal to 4. Since 4 is not less than 4, we'll skip out of the loop, and then we'll back off. And we're done. As you've noticed, recursion is really simply a loop that is created using methods. This example will show how recursion pushes methods onto the stack as it descends and pops them off the stack as it returns. We'll start off by showing the function that we've been working through, and we notice that in the debug method that the current line of execution is in purple. We notice that we already have the main function on the bottom of the stack. We'll first call foo, and we'll notice how foo puts it onto the stack. So we'll see main is at the bottom of the stack, and we have the function foo at the top of the stack. We notice that x is equal to 1, and we'll see that we've popped up our first foo onto the stack where x equals 1. You can see that here in our expressions debugger. We'll step through, we'll print it out, and then we'll call our next step, foo2. So notice we have 2 foo functions on the top of our stack. At this level, x is now 2. So we can see this in our presentation here as we're tracing through it. I now have 3 functions, main at the bottom and 2 foos, and x is different at each one of these levels. We'll continue on. We print out x again. We step in. Now x is equal to 3. We have 3 foos on the stack. Then we'll get to our top of our stack at 4. So we'll notice that we've popped 4 different copies of foo onto our stack, and we're tracking it. Now here in Eclipse, notice at the top of our stack the line is purple, but if I click on certain lines in the middle, I can see where I've left off. These are the places where I'm waiting for the method to return or come back. You can see them in kind of a teal here. And you notice also, as I click on each line, you notice that the value of x changes. So here, just at the top of the stack, x is equal to 4. If I go one underneath, x is equal to 3. If I go one below, x is equal to 2. So you notice that it's got a different copy of x at each point in the stack, and it means something different. Now I put this little placeholder here so we can step out of the stack and have a place to see as we start popping the methods back off the stack. So here at the top of the stack, I'm here, x is equal to 4. Now 4 is not less than 4, so I'll skip over this and do nothing. So here I am, I'm going to start popping things off the stack. I'm at the end of the function, and now I've popped the first one off the stack, and I'm back at where x is equal to 3. Alright, it's going to do nothing right here. I'm going to continue on. Let's pop that off the stack. Now I have x equal to 2. Notice x is equal to 2. And then I go again. I pop another foo off the stack. I'm back with 1. And main. I exit out my last one, and that leaves me at the end of main, and I'm done. So you can kind of see how recursion works. I essentially call myself, and it keeps track of where I am as I go through the stack, and as I finish the functions, it'll pop them back off the stack. Now that we've gone through the example of how pushing and popping the method onto the stack works, we're going to go through a way that you can trace recursive functions. Here's a simple function. What's the output of this function? So you notice here in main, we're going to be calling trace1 5. So let's step through it. First off, we'll use this notation fn1 to say this is the first time through the function, and we're passing it 5. We're going to hold on to all the variables that are passed in or changed within that function. So right now the only variable we're tracking is x. X is 5, x is not less than or equal to 1, so it'll skip over this if statement, and then it'll return this, and it's returning itself plus x. So what does that mean? It's returning the call to itself plus 5, and we'll hold on to this. And we'll keep track of where we left off. And the next time through this function, as we come back into trace1, we're now passing it a value of 3. The second time through, we're passing it a value of 3. We're holding on to 3, and we check this. If x is less than or equal to 1, well, 3 is not less than or equal to 1. So again, we'll go back to this point right here. And we're going to call function again. Third time through the function, we'll just call it fn3 for now. And we're passing it 1. X minus 2 is 1. Plus 3, which is 3, so we're holding on to that. And we're going to keep track of a third run. Here we're saying fn3. The third time through, x is equal to 1. 1 is equal to 1, so it's going to hit this base case and stop. So here we are, we're returning 1. Alright, we're here in the third value. We know the third time through passing 1 is 1. So we'll take that value and substitute that back in to the placeholder. 1 plus 3 equals 4. Now we know fn2 returns 4. Plug that back in to here. 4 plus 5 is equal to 9. And we find out that 9 is our answer. So that was a fairly simple one. We'll do the same thing, but now maybe a function with 2 variables. It gets a little tricky here, but we can do the same steps. We'll start off. We're passing in 4 and 3, keeping track of 4 and 3. Y is not less than 1, so it skips over this one and calls trace 2x y minus 2 plus x. So what does that mean? We stop here. So we're going to call itself, passing in 4 and y minus 2. 3 minus 2 is 1, so we're passing in 4 and 1. And x at this point is 4. So it resolves to this, fn2, and we'll keep hold of that and call it the next time. Now we're passing in 4 and 1. 1 is still greater than 1, so we're going to skip over and do this, run this. We're going to land on this point again, and then we're going to call itself again, but we're passing in 4. 1 minus 2 is negative 1, so we're going to call 4 and negative 1. We're still adding 4 to that value as x is still 4. Alright, this time through, we're looking at this. Now y is negative 1 and it's less than 1. So we're going to hit in this case, and we're going to return x. X at this point is 4, so we're returning 4. Alright, now that we have the return value of this whole function, we'll substitute it in to the previous one. We'll get rid of that. 4 plus 4 is 8. Now we have the whole value of this. 8 will return back here. 8 plus 4 is 12, and we'll find that the answer is 12. Okay. Now, we'll notice one other thing about recursive functions is that it really matters at what time you call the recursive function. Notice here in the before, we'll actually step through this, and we'll notice that before and after is really the same thing. It's the same thing. We have a base case, and we're calling itself, but where we print is different. So here I'm printing before I call the recursive function. Here I'm printing after the recursive function. And you can see that the output is different. You'll see that the before, it prints in order, and after, it prints in reverse. So let's step through that in this code. All right, so we're going to run the before, pass it to 1. So we print out 1, then we go into it, print out 2, go into it again, print 3, go into it again. Now if we hit 4, we skip out, and we're done. So we printed it out as we're going into it. Now with after, it's slightly different. We're going to go into after, and then we don't print it out right away. We go into the next call. Then we go into the next call, go into the next call, and as we step back out, we're going to be printing out 4, 3, 2, and 1. So it's very key as you trace through these functions, you really keep track of whether the recursive call is done before an output statement or a calculation, or if it's done after, because it really makes a difference. Now you can do the same thing with strings. So we'll go through another test case with strings. So we're passing in bat, and we're not quite sure what this does. So we grab length. Length of this is 3. Since 3 is greater than 0, we're going to land here. So we're going to call mystery of val substring 1. So substring 1 is starting at the first character. Remember that a string is 0, 1, 2. So the substring 1 means I'm starting at this character and going to the end, since I don't have an end value. So I'll be hitting at. I'm chopping off the beat with this function. Now this function, because we're doing this first, we're going to be doing the recursive function before we call this second function. So we're holding on to this second function here. We haven't calculated the value of that yet. We'll calculate it as we come back. So we're still holding on to it, and we're moving on. We're calling that function. Now we're passing it in here with at. At length is 2. 2 is greater than 0. We're back over here. We're going to be chopping it off again with t, and we're still holding on to that function here. We'll be calling it again with t. Length is 1. 1 is still greater than 0, so we're back into this function a third time. And we're going to be returning empty string. So here we'll return call itself with empty string. And this should be our last time through. Length will be 0 at this point. Since length is 0, is not greater than 0, we'll skip over this and return an empty string. We've hit our base case, and we return empty string. Now as we come back and set the values back, we still have to calculate this value of substring. Well, the value of the substring at this point, val is t, substring of 0, 1 is the first value of the first character of t, which is t. So we resolve that to t and return that back, so we're just returning t. Now we're going to take a look at this over here. We're going to return the first character of at. which is A, so it'll be T plus A. We'll return that back. So now we have T plus A, and we take the first character of bat, which is B. We'll return that, and the final output will be tab. This concludes the first part of recursion. Thanks for watching.